Hello, I'm Laura Cassidy from the American Chemical Society. Welcome to this media briefing from ACS Fall 2021. We're joined today by Dr. Brian Agee and Amina Aly from Augusta University. They're developing methods to make nylon 6,6 greener without zinc. Dr. Agee?
Yes, I'm Dr. Brian Agee from Augusta University. I'm a lecturer here, but in my spare time, I do green organic synthesis research. And today you'll be hearing from one of my undergrad research students, Amina Aly.
To begin this presentation, I would first go over the why behind our investigation and its importance. To begin, you can see from these three pictures, not looking at the synthesis, not looking at the mechanism, you have a tire, stadium seats, as well as skiing equipment. All three of these products all have something in common, and that is that they use nylon 6,6. The reason why they utilize that is because nylon 6,6 allows them to withstand harsh climates as well as any sort of stress that may be put on by the user or the equipment around it. We're focusing just on the first step at the moment because our whole goal is to make this entire synthesis greener and more efficient. To do that, we have to first start at the very beginning and focus on how we can replace zinc as the reducing agent and catalyst of the first step. And then once we satisfy that requirement, then we would move on to the second, third, and so on until we go on and actually produce nylon 6,6 itself. And in the next slide, I could talk about the metals that I will be using. On the two pictures on the left, you can see that there are two periodic tables from ACS. Outlined in black is zinc on both of them. Zinc is in the red, which means it is 50 to 100 years away from extinction. And in the green outline, you can see the metals that we will be using. We will be using aluminum, copper, nickel, cobalt, iron, as well as ferric oxide, which is also known as rust, a derivative of iron. We have two apparatuses that we'll be using, which you can see on the upper right-hand corner, an indoor and outdoor one. They're both, the setup of both are the same, excluding the hot plate used in the indoor technique, as well as the indoor condenser. In replacement of that, we use a solar dish to heat up the reaction using the power of the sun, as well as a water-saving condenser, which instead of using traditionally cold water to cool the reaction, we're instead using a heat transferring agent, in this case propylene glycol, to absorb the heat from the reaction when it's in its gaseous form, to convert it back into liquid, to go back into the reaction flask, preventing any loss of product. And how this satisfies the principles of green chemistry studied, I can talk about in the next slide. In the left, you can see the principles of green chemistry listed. In black outline, I have the ones that are being focused on in this investigation. To start off, we have less hazardous synthesis. Currently, zinc is being used, which is hazardous to aquatic life. Copper is also hazardous to aquatic life. However, we're using it as a potential alternative just due to the fact that it is not as endangered as zinc and could save the element from extinction. Nickel and cobalt, however, are not hazardous to aquatic life, though they do pose a health hazard to the experimenter. This, however, is not that big of an issue because with proper PPE, this can easily be avoided, meaning that it really isn't an issue to the experimenters. So if the yields are great, then it's not an issue. With aluminum, iron, and ferric oxide, aka rust, those would be our ideal choices as they are not toxic to aquatic life whatsoever. They pose the least potential hazard to the experimenters, and they're also not endangered at the moment. In concerns with design for energy efficiency, we are using the solar dish. In doing so, we're using the power of the sun in replacement of electricity, eliminating the use of a hot plate and the burning of fossil fuels. With the use of renewable feedstocks, this is also again satisfied by the use of solar power from the sun by the solar dish. However, it is also satisfied using the water-saving condenser. And this And to put this into perspective, using the Liebig condenser as a model in Augusta University's lab, which fits 20 students, the Liebig condenser consumes about 1 to 4 liters of water per minute. And with 20 students being in one Augusta University organic chemistry lab, this eliminates the potential use of 1,200 to 4,800 liters of water. And if there are any questions, I'd be happy to answer them.
Thank you, Amina. And now I'd like to ask you a few questions about your work. First of all, how did you get the idea for this research?
I'll pass that one on to Dr. Agee, as he's the one who gave me this project.
One of my main goals as a researcher, since I'm a lecturer, I like taking reactions that we can use in an organic chemistry lab or a general chemistry lab and try to modify them to make them more safe and more environmentally friendly, because I am a green chemist. So that's where it kind of started. I was looking through the Journal of Chemical Education and saw a synthesis for nylon, and we started building it from there. And then with my knowledge of just, the endangered elements list I saw with zinc being used, this was a good place to start in trying to modify this reaction.
Okay. So in the term nylon 6,6, what does the 6,6 refer to?
Yes, the 6,6 stands for, there's 2 monomers that are used in making of nylon. It's the 2 monomers that are made contain 6 carbon atoms each. That's where the 6,6 gets its name.
Okay. Is zinc used only in the first step of nylon 6,6 synthesis, or is it used in other steps?
It's used just in the first step, just to get to that cyclohexene component.
Okay.
And then other metals are used throughout.
I see. Do you need a hot, sunny day for the solar reflector to work?
Absolutely, you do. We are in Georgia, and Augusta specifically's weather is not very predictable. So we've run into a lot of occasions where the weather is just not ideal. So we can't do a solar run at the moment, and assuming the weather's terrible. So we just do as many indoor ones or literature reading or just something.
Right. Okay.
And also on partly cloudy days, we found, because this is what I used for my graduate school work, was my research mentor, Dr. Dan Swartling, came up with the idea to design this solar reflector, and I've kind of carried it through because I love working with it. You can actually get it to work on a partly cloudy day, as long as the sun is producing about 650 to 700 watts per square meter of solar radiation. You can get a reaction to work pretty well.
Okay. Are solar reflective dishes and water saving condensers something that could easily be incorporated into, the industrial manufacture of nylon 6,6?
I think absolutely, yes. I mean, you would need a large area. The indoor condenser specifically, you don't need it to be outside even. I mean, I think we could even use them in our organic chemistry labs in replacement of our traditional ones. We would just need the funding to buy them. But the only one that poses just a bit of an inconvenience would be the solar dish, just because of its size, but it's still a possibility.
Okay. You mentioned that iron can substitute for zinc in catalyzing this first step of the reaction. Is it about the same efficiency, or is it a little bit, less efficient than zinc?
We have actually gotten some pretty great results so far with using iron. Currently, zinc, when using it indoor, is about 80%. Ideally, and this is also if you're going in the literature and past experimenters with iron, especially actually when we're doing our outdoor trials, it's actually 78% yield, which is pretty much the same, and it's perfect if you're just trying to replicate the amount produced and then work into purity.
Have you tried using ferric oxide or rust as a catalyst yet?
Not yet. We have been in the process of moving buildings. We were originally on the Somerville campus. Now we are at the health science campus. And we have had to move equipment, offices, you name it, we had to move it. So nothing is set up right now. If it is, we're not allowed to use it yet. So once they are set up, we're hoping to get in at least 1 or 2 trials of rust to have for the conference. But as of right now, we just have zinc and iron.
Okay. Do you plan to try to make other steps of the 5-step nylon 6,6 synthesis screener?
Yes. Yes, we've already got in our kind of mapped out schedule for what we're going to do next, what we're the second, third, fourth step in the whole process to make it to nylon. We kind of have ideas of where we want to go, but this first reaction keeps providing more and more good little cookies of leading us different directions of where we're going to go. So we're not getting off of this reaction yet because it keeps giving us interesting ideas of, ooh, what if we try this?
Okay. And to conclude, what do you want viewers to take away from your talk? What's the key conclusion or message?
It's a lot easier to make things greener than you would think. I know before I got into research with Dr. Agee, I didn't know that much about green chemistry other than what I'd read in ACS or just from just articles around online. But I mean, the water saving condenser is a great example. We can easily put that in our lab in replacement of the sink. And yes, you'd have to spend some money on it, but either way, you're going to be spending that money on those things. So in the long run, you are saving a lot of water. I mean, in just one classroom, you're saving 14 to 4,800 liters of water. And when it comes to industrial component, you can also use an outdoor setting, and that may even be cheaper and more efficient for them.
Thank you. Media briefings for ACS Fall 2021 will be posted throughout the meeting at www.acs.org/ACS Fall 2021 briefings.